Hello and welcome everyone. Thank you for joining us today for our webinar titled What's New in H2O Driverless AI. My name is Patrick Moran and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Arno Candel is the CTO at H2O.ai. He is the main committer of H2O-3 and Driverless AI and has been designing and implementing high-performance machine learning algorithms since 2012. Previously, he spent a decade in supercomputing at ETH and SLAC and collaborated with CERN on next-generation particle accelerators. Arno holds a PhD and master's summa cum laude in physics from ETH Zurich, Switzerland. Before I hand it over to Arno, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the Questions tab. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. Without further ado, I'd like to hand it over to Arno.
Thanks, Patrick. Thanks, everyone, for joining today. So the team at H2O AI has been very prolific and innovating in the last few years. As you've seen, maybe we've been named visionary in 2 Gartner quadrants just this last few weeks. One is for data science and machine learning platforms, and one is for cloud AI developer services. So this reflects basically the drive that we have as a company to bring AI closer to the people everywhere in the world. We democratize AI, we make platforms available, both open source and enterprise solutions for machine learning, data science, and soon there will be even more vertical products coming out with our Q platform to write smart applications. And in this demonstration today, it's all about driverless AI. So the team has done a lot more than just driverless AI, but this is the thing we focus on today. It's one of our flagship products, if not the flagship product. It is AutoML for the enterprise. It's really automating a lot of things that you can automate, right? You put in the data set, and out comes basically code that you can put in production with a model that predicts whatever you want it to predict. Let me show you a demo of this. So this is, I launched this instance from Puddle. That's another service we have to create systems. So you can just say, I want to launch a driverless version, this and this, on this kind of instance, and off we go. So I did that. I got this machine here. I uploaded some data sets. These are all Kaggle data sets, or all but this one. This one is a prototype data set I made that just has a bunch of random data in it: customer IDs, timestamps, 2 random columns, and some outcome. And this is a demonstration of how we can take this data and now modify that data inside of driverless with a Python recipe. So I can just upload a Python snippet. This Python snippet is code that I have on my computer here, and it says take data that was created randomly here and convert it to non-transactional data. So instead of having timestamps and random transactions, I now make group by aggregations with moving windows over time to get the mean of the outcome as a function of the last 10 days. So there's windows, and in those windows, I compute means over the outcome. And so when you look at this new data set, we still have timestamp, we still have these 2 random order features, we still have the outcome, but now we have these extra features that are created, let's say the maximum of the target in the past 5 days, or the mean of the target in the past 5 days, or the mean of the target in the past 7 days. And as you can see, this was code that was written here in Python on my laptop, and I parameterized these window lengths and so on in this code. So this is totally arbitrary code you can upload that creates data inside of driverless AI to convert any data you might have from anywhere into new data. And that can be used not only to create new data sets on the fly, but you can also write your own connector, right? You can connect to JDBC or whatever you want to do. That obviously we already have. If you go to our fully fledged version here, this has all the connectors already in there. So JDBC is one, Snowflake is one, Minio is one, KDB is one, Google Cloud is one, Blue Data for IBM, Azure, Hadoop, Amazon, everything is already connected out of the box. But you could have your own connector that pulls in something specifically from somewhere, let's say you download it from the internet, you want to join a few tables, all of that you can now do with a data recipe that you upload or that you provide the path to. As long as this is a file server that this instance can reach, it will just make data on the fly. So it's a pretty nifty system. This is one of our recipe architecture pieces, in this case for data. You can also have recipes for models that are being trained or for data transformations. We call that feature engineering. You can also make your custom KPIs. Let's say you want to compute the cost for a marketing campaign. You can directly optimize this cost. So there is a lot of things that you can do with Driverless AI, and I'm just going to briefly go over all these things. So for example, now that we have these transactional data sets, we can not only look at them, we can also visualize them, or we can split them, or we can predict them. And if you visualize it, it will basically compute some statistics. And I can show you some other statistics too, credit card, or this is a rental data set. They're all just plots of interesting things. So in this case, you can see there are some correlations, some outliers, and which ones are the outliers in my noisy data set? Well, there are a couple on the outside because it's small data, so it still thinks some of them are outliers, but really it's a Gaussian distribution. There's a correlation graph. You can see what's going on here between the different columns and so on. So this is only interesting stuff that is shown to you directly. Now that I have this data set, I can say, okay, predict. What do you want to predict? Well, I want to predict the target column. And I have a test set. Later, we can compute some scores on it once the experiment is done. And as I say go, that's it. It starts and makes an experiment. And why do I say experiment and not a model? Well, because it's not just one model that we're training, but we're training many models. We're actually training sometimes hundreds or even thousands of models, and we're doing thousands of features on the fly from that original data set. So not only do we now have lags created by this recipe, we also can do interactions of these lags, clustering, different encodings, embeddings, all kinds of stuff. Obviously, for time series, we also have a built-in time series recipe that you can use for time series that have a uniform time, such as weekly store sales, as in this Walmart example here. So the Walmart data set had weekly sales for every moment in time over weeks. Every week, there is a number for every store and every department. And it automatically figures out that stores and departments are the grouping items in that data set. And then it automatically makes lags for these different stores and department sales, looking back 40 weeks, 44 weeks, 50, and so on, 51, 52, 53. So it knows 1 year ago is an important moment in time. And it does the exponential weighted moving average of those lags of the sales from a year ago. And it also does the first order derivative of the sales, so that the change of sales between weeks from a year ago is also important. And those are features. Then we have, of course, features like the year, the day of year, and so on, or other features that are provided by the data set. And once this is done, we can interpret this model and look at it, and we can say, hey, look for store 1 and department 4, what's my prediction into the forecast horizon? And you can even ask, why is there going to be a peak here? Well, it will explain that because this bar says 52 weeks ago, there was a lot of sales in that store and department. So you have an explanation for every moment in time, for every row even, why there is such a predicted value. And when you add up these bars, you get the actual number, the sales numbers. So you can actually do math on the output regression number and say, this is why your house price is up by 10,000 this month, because we think that this feature here has increased since last month. So we can do really good model debugging. Not only is it the system, you have a bunch of experiments, you have data sets. You can also make projects where you can list different experiments together. So I have here some projects, only one in this case where I have some data sets and one model. I could make more models, and once I have them all here, I can compare them. And I'll show you that in the slide deck. So let's go and start a quick experiment. One on a Kaggle data set here. This one is the Paribas data set, 100,000 rows. I want to predict the target. Here's the test set. Test set does not have actual outcomes, so we'll just make predictions so we can submit them to Kaggle. Kaggle said we want to optimize the log loss, so they'll do that, and I will say go. And then later we can go and look and see what happened. So let's go back to the slide deck. Driverless AI is really an automatic machine learning platform for the enterprise, which means it is very robust, it is very scalable, it has built-in data management capabilities that are very good. It's using data table. Data table in R and in Python are both created by people at H2O AI. And data table in Python is used extensively for driverless AI. It can read and write CSVs to disk, from disk in gigabytes a second. It can do grouping, aggregation, joining, very, very fast, multi-threaded C++ backend, all programmed from Python. So we are writing driverless AI in Python, but it's using all the C++ backends, such as XGBoost, LightGBM, CatBoost, and so on. And also H2O models, open source H2O models in Java. And you can have custom scorers, custom models like CatBoost here. You can have custom transformations, like you can say, I want to join in whether or not a given date is a holiday in your country or not. That is a custom recipe for your country. You can have longitude, latitude transformations that are specific to your domain. You can have translations of like codes for healthcare, what they actually mean to text, and then once it's text, you can do embeddings on them or sentiment or whatever it has to be, right? You can really customize this whole transformation process. So this is a tool for data scientists to become more productive. This is not replacing data scientists, quite the contrary. It's like giving people cars to drive instead of being farmers with shovels in their hands, right? Now we are giving them a tool so that they can be more productive. And it produces automatic scoring pipelines. So every model that is built, every single model that we build here at the end of an experiment, the final pipeline is converted to scoring code, which is production-ready, low latency scoring engines that can be deployed in Java. That means Windows anywhere, in the cloud, on-prem, any machine you want, or C++, which means you have a native integration into Python and R, or C# or anywhere you want to score C++, low latency scoring engines. And those engines are not just the models, but they're also the feature engineering. So any of our built-in transformers that you have enabled by default, of which we have about 50 or so or even more, those are all converted to Java or C++ scoring code. And that is very powerful. And of course, we use GPUs and we use everything we can on the hardware, right? All the RAM, all the CPUs, all the GPUs that you have are being used. And since it's a general purpose machine learning platform, it can be used across many industries, especially financial services, telecom, marketing, healthcare, you name it, everybody needs this machine learning capability. And that experiment that we just started earlier should eventually get to 10th place in Kaggle out of the box, out of 3,000 competitors in Kaggle. This driverless AI model, when you set the settings to 7.10.1, gets you to 10th place out of 3,000. So that's a pretty good percentile score, right? It's as good as Dimitri was back then 2 years ago or 3 years ago now when the competition was held, maybe even longer. That is still a good place, 10th place. And that 10th place was hard earned, right? It took them 2 months to get there, and driverless does it automatically. So there's a lot to be learned from this tool. And when you look at it, what it returns you which features were good, and it tells you which models were good. And it also tells you if there's leakage in your data or if there's a distribution shift in your data. It gives you lots of warnings and explanations about what's going on. So the power is really in enabling the data scientist to quickly understand their data and to see if the model makes sense. So since we've shipped driverless LTS last summer, we've added a lot more in the latest long-term support version 1.8 that's out right now. And then later this year, we'll ship 2.0 LTS, which will even add more So let's see what we had in 1.6 so far. So we had these Grandmaster recipes, Kaggle Superstar recipes. We have over a dozen of Kaggle Grandmasters at the company, right? They're helping building these recipes. They're built into the system. We have all different types of machine learning models, including neural networks, deep learning models. But more than that, we have the data science tricks of the century, if you want, all the tricks that you can imagine. We have machine learning interpretability, leading edge techniques to explain the models, sensitivity analysis, disparate impact analysis, Shapley values, and so on. We have automatic report generation. At the end, you get a Word file, 20 or 30 pages of Word file that tells you everything that happens. So you don't need to worry about writing it all by yourself every time. You saw the automatic visualization, and there's going to be another version of that coming out soon that is even more customizable. And by the way, this visualization, you can also do it from Python via the client API. And all of driverless can be controlled from Python or R via client API. So every click I make in the GUI, I can make from Python or from R as a programmable code client API. So that means the users don't have to just click, but many, of course, like to click around, including me. The data connectors, I showed you the list. You can import anything from anywhere, but you have to understand the data goes to that node that's running driverless AI. Currently, it's a single node, so it's one node with 4 GPUs or 8 GPUs or 16 GPUs or no GPUs, depending on the problem types that you want to run on. It can have 4 CPUs, or it can have, no GPUs, whatever you want. But we'll take advantage of everything that you give us. This is the benchmark for data table. Let's have a quick look. You can see here for 50 gigabytes, data table is the fastest, right? Faster than Spark, faster than ClickHouse, faster than many other tools that may run out of memory. So it's definitely something to consider if you want to do group buys and joins on big data. And you can see here how it behaves in time. And this is an open source benchmark that you can run yourself. So let's go back to the slide deck. The other thing that I wanted to mention is there's 2 scoring engines that come out. One is the Python scoring engine, which is basically a pickled state of the internal pipeline that we are fitting with all the feature engineering and the models in Python, the way we call them, with all the pip installs done for you. So you need to have an internet connection, and then you can run the same pipeline that comes out of driverless as a Python code, native Python, if you want. Pip installs it for you, makes an environment, and runs batch scoring job, just like when you say in the GUI, score me another data set. And then there's the low latency Mojo that comes out, which is a protobuf file that contains all the state of the final pipeline. But there is no Python there. It's just the definition of the pipeline. And then we have 3 runtimes to interpret that state. One is in Java, one is in C++, but has 2 wrappers. One is R and one is Python. And currently we don't expose the C++ API per se, but if you wanted to write a Go or a C# API for that, let us know. We can talk about that and we can help you with that, or we can implement it ourselves for you. There is, of course, authentication security. Now we have single sign-on as well, where you can connect to driverless in a secure manner. You can also upload the outcoming artifacts to a secure location without having to download it to the laptop that you're working from, for example, or the workstation. So there's all these security considerations for enterprise that we're doing. And the standalone C++ scoring engine will support PyTorch, TensorFlow, FTRL, and so on, where the Java version has to call down to JNI, to the Java native interface, to call these methods, right? So Java will not be as portable as pure Java once it calls TensorFlow, for example. Then you need to have a compiled version of the TensorFlow library, even though you're using Java. You would have thought Java is portable. Yes, it is, but as soon as you're calling down to these native things like PyTorch or TensorFlow, you need to have a native library shipped. And in the next version of the shipping, we will have TensorFlow for Java, but only on x86. And at some point, we might have Mac versions and PowerPC versions as well. Currently, we have Mac and PowerPC and Linux bindings for C++, but not for TensorFlow yet. Tensor was only for x86. So talk to us if you want to put models in production for a specific version, if it's not yet supported. I mentioned the project Workspace and the single sign-on. There's the R client that we now have in addition to the Python client. And the next version 2.0, that's going to be the big one of this year, which will have storage of models. So once you have a good model, you can push it to a remote storage, and then you can get other people to pull it from there. And so that's how you share models. And then there will be a multi-node mode where you can train models on multiple nodes, not only to be faster, but also more data at some point. But the first edition will be faster. So that means, for example, I can have 10 nodes for my driverless instance, and when I say run these 7 experiments, they all can go wherever they need to make it run at the same time, instead of all sitting on the same memory and the same CPU, same GPU. And then there's a model management component where you can see how the model is performing in production, whether there's a shift in the distribution, whether the model has to be retrained, and so on. And also we're working on PyTorch backend. We already have a module for that, so it's not too hard to integrate. We will probably do that in the next few weeks. And then in 1.9, the preview for 2.0, we will have BERT models out of the box. And then image segmentation and so on will come shortly. We have a private preview for that if you're interested, for image models using TensorFlow or Torch. So what's new in 1.8 LTS is that the recipe architecture, where you can write custom data and custom models, custom transformers, custom scorers, KPIs, all that is now long-term support, which means we'll be able to support you going forward. Anytime you have a new version in this LTS release branch, all your old models will still work just the same as before, which means you can always create new modules, create auto reports, you can do interpretations of the model and so on, without having to worry about any upgrades breaking these models. So as long as you stay in 1.8, you'll be fine. There is a visualization of the pipeline and constant models and decision tree models. I'll show that to you, the scores tab. So let me go and show that to you right now. That seems like a good moment in time to switch over. So here we go. This model is running now, and you see it's already at 44 log loss. The winning solution was 42.9 or something, or 43 that we had at 10th place. So at some point it goes down, and then it drops even more when we do the final ensemble. Let's go to an experiment that is already done. For example, this one, 2 sigma rentals. So that's a data set that has a 3-class problem, and you want to predict the interest into the rental property based on price and who's the manager, and the features that are describing this text, or the text features that are describing the property. We're having a CNN model, deep learning model here, TensorFlow, embeddings trained from scratch, as you can see. And that model has also access to bedrooms and so on, and longitude, latitude, all that. And if you look at the model, what is it? There's actually 4 models that are 4-fold cross-validated, and then stacked together to make these 3 output prediction columns. If I look at one of these models, you'll see that these are the original features. And for example, the features themselves here, this is one column is called features coincidentally, and that feature column is what is in that apartment, right? It will have text. And you can see that we do a CNN on that. And we also treat it as a string and do target encoding on that categorical, but it's obviously maybe this one is not as useful as this one, but the model still took it as an input and it can still work with it. So sometimes people have the same description or so. And we have TF-IDF as well on the description. And if you had run this experiment a little bit longer, maybe it would have done a CNN on the description field as well. So this is a nice way to visually see what's going on. And why weren't the bathrooms used? Well, maybe it wasn't important enough, but maybe this was just not the best experiment. So when you go look back, you see our time was 2. The whole thing ran in like 10, 15 minutes, so maybe it's not the best model. What's also interesting is, the constant model made a 78 log loss with constant prediction. So I know that my 55 is already a lot better than a constant. Sometimes that's non-trivial if you have like an F1 score or something where You can be misled by a 0.95 F1 score, but that's actually easily possible if the model is a constant too, depending on the distribution of the target. And that's where we do scores here. We show you all the scores of all the different models. So you see Light GBM, XGBoost, GLM, constant. You have a comparison of all these models, and you see the log losses. And there's more things like, you know, how many features were used, how everything is here. There's no secrets, right? We're just doing tuning for you. And then if you go down, you can even download this data. If you go down, you can see the final pipeline had Light GBM and a constant model. Now, why is there a constant model in there? Well, we're throwing it in so that you can see how bad it is comparatively speaking to the other model. And then hopefully it gets a weight of 0 at the end. And that's exactly what you wanted in this case. The blender in the ensemble said, I only want Light GBM, I don't want a constant. That's because it is so bad, because the log loss is so much worse, 78 instead of 65, right? And this is a validation for your logic overall that everything is sane. You get the 4 folds, you get their scores of all the different metrics across these scores, these folds. You see how many rows are in each fold for training and validation. And all of that is basically exposed to you in a visual way now. That's new in the LTS branch of 1.8. So this should definitely help you understand what's going on, even more so than in the past. People have asked, like, why do you pick this or that model? Well, this is because we tune and we use a genetic algorithm over time that gets smarter and smarter. It makes different features, different models, and they all mutate and evolve over time. They learn from each other. And in the end, the best thing that comes out, the best pipeline as judged by a score that's using your scorer, if you have a custom scorer, otherwise it uses whatever you select in the listing there. That scorer is optimized. But if you have a high interpretability, then we might actually optimize the model complexity too, right? If you say I want a very interpretable model, we're trying our best not to give you 600 freshly made features that are all crazy embeddings and clustering and so on, then we'll just keep the number of features low. So it's really an optimization in the overall space of what you kind of wanted. And as you remember, there are 3 knobs. One is for accuracy, one is for time, and one is for interpretability. If you have high accuracy, that doesn't mean the model will get better necessarily. It just means we try harder. And how much time you give us will also affect how much we can try. And then the interpretability will basically say how complex the model should be. So this is inverse complexity. You do 10, you get a GLM or a single decision tree. And if you do 1, you might get many, many features and a stacked ensemble. But also if the accuracy is high, we'll do more ensembles, more cross-validation. Basically, the accuracy means how much effort we put in to figure out whether the model will be good at generalization performance, right? And for that, we need more folds, we need more data splits, we need more, for time series, we will have more moving windows for backtesting. And that's all just the effort we put in making sure that the model that comes out is actually good, that our scores are not misrepresentative of the truth. So that's the accuracy. Time is saying how long should this evolution run before you consider it converged and good enough. And interpretability says basically how inverse complexity should be. And obviously you have a lot of choices to configure it still, right? If you say, I don't like it the way it is, you can, for example, say, I want to rerun this experiment here. The same model with the same parameters, just another name for the model. And maybe I want to also change some expert settings. We can go in here and say, let me see, for GBM, what do I have? I can do here in the model tabs. That's all that has to do with GBM. This is what has to do with GBM. So there is a correlation beyond which we trigger monotonicity constraints. So this is something that's a feature related thing that has to do with GBM. Because it only works for GBMs right now, this monotonicity constraint. We can set the number of trees. We can say whether XGBoost is on or off, Light GBM is on or off, and so on. Which boosting types we have for GBM. So there's lots of features, right? If you want to look at TensorFlow, these are TensorFlow options. For NLP, we have CNNs, bidirectional GRUs, character-based CNNs, pre-trained or non-pre-trained embeddings. We can train them from scratch, and so on. So there's a lot of choices in the expert settings that you can use to fine control the experiment. All right, let me move through the data connectors. We've seen them before. The custom data recipes is what I uploaded, but you can also have a live window where you can type in stuff, and then out comes the preview, which is really cool. Once you see that this is actually computing mean, min, max, and so on as you set up here, then you can say, I like it, and you can save it, and then the whole data set gets transformed that way. So this is a live code preview to do any types of operations on your data, anything. You can download stuff from the internet, group by, join, augment, whatever you want. This we've seen. The feature engineering we've seen, so all this cool clustering, weight of evidence, interactions, everything is there, and that's one of our secret sauce. Another secret sauce is the fact that we don't overfit easily because we have a lot of guardrails in place. We build lots and lots of models in this genetic evolutionary algorithm, and we use GPUs and CPUs, we use deep learning, we use statistical elements. Trevor Hastie and Rob Tibshirani are advisors to the company together with Stephen Boyd. So we know what we're doing in terms of statistics, and in terms of deep learning, we have all the Kaggle Grandmasters helping us figure out what techniques are useful or not. We also have deep learning recipes for time series, not just for NLP or images. These are the expert settings. For time series, obviously, you need to do lag-based features, and we also need to do moving windows with potential gaps in there, and the forecast horizon has to be correct, so we allow you to control all that. And we're working on making time series work for even very small data. Some customers have 100 rows, right? They say, I have 100 monthly data points for the last 6, 7, 8 years, and that's all I have. Predict me the next 2 months. And that is a different recipe than the statistical recipes we've been using for big data. For NLP, we have many, many techniques. As I mentioned earlier, BERT is coming in the next edition. Really a strength of the company and the product right now. MLI as well, leading machine learning interpretability. Disparate impact, you can really see which groups are affected how much by every model that you're looking at. So you can go into a lot of detail to figure out everything about your models. And we also have the what-if analysis and the NLP for MLI here, so you can actually see which words were helping you make the model predict more like a yes versus a no for this particular observation, for example. So this is quite useful to see what's going on with the models. This project workspace I mentioned, you can have different models that you run with or without custom recipes, and then in the end you can compare them all in a visual way, look at their ROC curves, look at their scores in the scores tab. You can definitely go deep as a data scientist. And as I said, you want to see the weight for a constant model to be 0. Sometimes the models that are non-constant models, like Lightyear XGBoost here, they could be, let's say if you have a low accuracy and a noisy data set, they could be a little bit overly confident, right? They could predict like a big probability or low probability too fast, let's say, even though they're actually optimized themselves. Maybe they're not really globally optimal. So a constant could still be added with a little bit of a contribution, and it wouldn't actually hurt the overall performance, especially if you, depending on the loss function. So it's not always a bad thing that you see the constant model get blended in, especially for ranking problems like AOC. It doesn't really hurt to add a constant, right? So you have to be, just looking at this guy a little bit gives you an indication of what's going on in your overall pipeline. So we like it as a good reference model. And again, as I said, there is 2 clients, so you can write code like this where you say run an experiment, you can do a for loop over them, you can do your own leaderboards and so on, everything with your 5 default models that you like you like 1 GLM, you like 1 GBM and so on. And we're working on demos for other platforms where we do that automatically. Then there's the module choices. You get Java, Python, R, as I mentioned before. And you also get the low latency for all of these 3, right? That's low latency. When it says Mojo, that means low latency. That means it's a single protobuf file that we use to make predictions. That's it. So you load the protobuf state and you make predictions. That's it on a frame. And that looks like this. The model basically has, as I said earlier, these pipelines. The whole thing is in that protobuf state. And when you score it, you load that pipeline Mojo file, you load a data set, and you say predict. That's all you need. No other dependencies, nothing from H2O, no GPUs. You don't need any, particular version of Python or anything. Just 3.6, I think, and up. And it's pretty straightforward. Low latency scoring. The same for R, and then the same for Java. We can also deploy these Mojos on the cloud. So this is using a Java Mojo that we deploy in AWS Lambda. So you just type in your credentials and upload it, and then you have a Lambda endpoint that responds. And there's also a REST server built into the actual driverless instance, just for like dummy, let's say, demos, where you have a REST endpoint that you can send your queries to, like the tweet content, and it'll return you the sentiment. And now again to the recipes. That's our big highlight of this year for Driverless AI. So we have data, as I mentioned earlier. We have the custom KPIs. You can make your own code that says, hey, I want to optimize the number of letters that I send times $1 minus the number of letters I expected to return per letter, and so on. And you can then optimize the return on your marketing campaign. You can have any models you want. Anything that has a Python API, you can make custom transformations, as I mentioned, with anything from Python. There's a whole repository that has currently over 140 recipes for joining, grouping, for models, CatBoost, DAL, Intel DAL, speed up version of XGBoost, SVMs, factorization machines, your custom loss function. You can even make your own gradient and Hessian for the XGBoost and LightGBM, so that you can directly optimize the tree splits for your custom scorer. There are scorers available that help with marketing or profit or false discovery rate and so on. There's time series, ARIMA, Facebook profit, you name it. There really is a lot. Embedding for text. This recipe repository has a lot. You can see here all the directories, and when you look down, we have a list of auto-generated, the list of all the recipes. So this website here is on H2O AI's GitHub, Driverless AI-recipes. So then you can choose, once you import these recipes, you can then choose which models you want, you can choose which transformers you want, which scorers you want, and then you see your names of your transformers show up here. But when you then get a deployment package at the end, that's then only the batch scoring that I mentioned in Python with the pickle that's saved. It's not actually going to be a Mojo, unless all of your recipes for transformers and models have a Mojo, which means you would have to implement the two Mojo method, which obviously most of our customers won't know how to do that yet because it's not the best API we have right now. So we are helping some of our customers to do that. The logarithm, for example, is easy to implement. If you have specific needs about what you want that you need in a low latency scoring API where you do single row scoring in milliseconds or microseconds, let us know. Otherwise, you will get a full pipeline that can score in batch mode for anything that you throw in, even your custom model, okay? So if you have your custom CatBoost, that will score just fine on your data. And you can compare these NLP models with and without sentiment and so on. That's the beauty of the project workspace. You can actually see the impact of all your custom features that you threw in. And here we have one for profit, here one for ARIMA, and here is our recipe that is lag-based and uses a gradient boosting tree or something at the end. The difference is that these profits and ARIMAs will just be black boxes, right? They make one prediction, and that's your feature, so to speak, that comes out as a number for every row, and we can't really explain which one is how strong. It's just that's what Facebook said, or profit said, or that's what ARIMA said. So it's harder to interpret those other models sometimes. And that's why our feature engineering is really not like a neural net where it's just black box prediction, but it's actually a bunch of features that each matter to a certain extent. That's already more interpretable, and that gives you, for these time series, Shapley contributions, as I showed earlier, a really meaningful thing that says here 52 weeks ago is most important than 53 weeks ago. So like last year's behavior matters the most. Whereas in Profit's case, you just get one bar that says this is my prediction, basically. And then there's the documentation, as I mentioned, the 20, 30, 40 pages that come out. They include everything, right? They include all the parameters that were tuned, all the models that were tried, all the, the final ensemble, the display of that pipeline. It shows you the partial dependence plots. It tells you why we dropped a column because it had a strong leakage, where it gave away the answer, for example, with 99% overlap, let's say. Super strong correlation, or R-square, or Gini, or AOC score with that one feature and the target. That means that there's a leak, and we can even explain to you that that's happened in that Word file. So you have a report that explains everything. And this is a private preview for the machine learning ops, where you can then compare champion challenger models in production. You can deploy them. You can do A/B testing. You can see if they're drifting and so on. And this is something that we're working on right now. That's in active development. So it's connected to the project page, where you can export a project from Driverless AI into this model ops view on a different machine, let's say. And that then has a way to deploy these mojos, these standalone production pipelines, to different machines. And then every time we score on a row, we record the actual distribution of that row, and we can then provide population stability measures of the distributions from training time and from scoring time, and tell you that there's a difference, that there's a shift, that it's time to retrain the model or to check the data pipeline. Great, so that's it for my presentation today. If you have questions, we have 10, 15 minutes now. Otherwise, I'll show more demos.
Yeah, thank you, Arno. So as questions start to come in, let's give folks, some time to start typing those in. Maybe you could start just going through some additional resources, since we don't have any to go through right now. And then we'll check back here in a little bit.
So this is our website, H2O.ai. There's a lot of blogs here, and also articles about our customers, what they're doing, and case studies and so on. You can see we have a lot of Grandmasters writing content. For example, the Super Bowl. There was a injury. Let me show you that. There's a blog about, let's see where it is, on the NFL, how players get injured. Might even have been this one. And there's John Miller. Yes, perfect. That's his Kaggle competition. So he really wrote an amazing blog with data science behind it, and won even a competition on that. And he had a webinar just a few weeks ago on that, how he reduced the lower body injuries in the NFL. Basically, he has analytics about that, and it's a very, it's interesting how you can do data science when you're starting to look at data for humans, right? Especially now with the coronavirus going around. We are expecting to contribute to that in a meaningful way in the coming days and weeks. And we have so much talent in the company, and these tools like Driverless AI that actually turn into platforms where you can do anything you want with custom recipes. You don't even need to restart them, right? You can just literally go here and upload another recipe as you're running the experiment. So for example, let me show you here how I do that. So let's say you want to do the credit card data set, and you want to import a recipe, and I want to predict age. And now I'm going to expert settings under the top, and I'm going to upload a custom recipe. So all I need to do is I need to go to my directory that has recipes. This is the Git clone of that recipe I showed you earlier, that Driverless AI, H2O AI / Driverless AI recipes repository. the whole clone. Now I can get a transformer, let's say numeric somewhere here, numeric. I can do the log transformer, right? And now it's being imported and sanity checked. It checks that it actually works for regression or for classification and so on. And all the problems that we will potentially ever run in driverless are being checked right now so that this recipe is actually good. If there was a bug in that recipe, or it would be for a wrong version of driverless AI, you would know, basically. It would tell you, hey, there's something wrong, and you will get the error message. Now that I imported it under recipes, under transformers, it's now going to be enabled. But next time I do an experiment, it's not enabled because it's only enabled when you freshly upload it. Otherwise, you would have too many enabled by default by accident, let's say. So I can just say, hey, I want to uncheck everything. I just want to have log and maybe original. And then let's see which one is better, right? And now I have here in my preview, I will see just log and original. And I see my other models that are being used by default. If I want to add different models, I can say, hey, okay, let me add the H2O models. So I go to driverless AI recipes, models, algorithms, and I take the H2O models. Now it's doing acceptance tests for those, and actually shortcutted that because they know that they're correct, so it's going to be a little bit faster. And now we can enable those also in the expert settings. So I can go to recipes, so here recipes, models, and now I have H2O models. So let's uncheck everything and just do H2O GLM and the built-in GLM, let's say. And now I have a bake-off between H2O GLM and our GLM and my log and original. Now our GLM I have to enable here first because by default it's an automatic, which might not be turned on based on the settings of interpretability and accuracy. So I'm forcing it on now. The GLM and H2O GLM and log and original, that should be the bake-off. And now I can run that, right? So you really can customize it as you want. And I didn't even do a custom scorer yet, but you can imagine it's the same way. And now it's running, and you can look at the GPU usage, the accelerators predicted, residuals, all that while it's running, right? And it's first looking at the leakage, didn't find anything. And it says here, what we're doing right now in the initial evolution phase is going to be less trees than in the final model. So don't look at these scores too much. Wait until the final score show up. Whatever comes out here is just a rough sketch of reality, right? It tells you that marriage log of that is a good feature. But you understand, of course, that that's a joke right now because the log of a number versus the number itself, it doesn't really make that much of a difference, right? However, for GLMs, maybe it does make a difference. For trees, it wouldn't, but for GLMs, it could. So now it tells you that kind of money should be logarithmic, for example. So the pay, the bill amount, all that stuff, logarithmic money is better than linear money for a linear model. So we'll see which one wins, right? And we have a bake-off between H2O GLM and GLM. And at the end, we'll see what wins. So this is how it works. It's really up to you to come up with ideas, and then this platform will tell you quickly what works or doesn't. You can also go to trace to see what's running. So there's 4 GPUs that are all running in parallel. These are the regular built-in GLM models. And then some of them are the H2O GLM models. When it's green, it's using GPUs. When it's gray, it's not using GPUs. So you can, and the red is the feature engineering. So you can see as time evolves, we're building different things. In the meantime, the other Paribas experiments have finished with our fast settings. So in 20 minutes, we get a 44.5 score, which is not bad at all. This is hard to achieve by hand. And the way it's done is with all these interactions here. You can see weight of evidence, cross-validated target encoding of these 6-way interactions. Right? 6 categorical columns are concatenated together into one new column if you want. Then there's 5 folds created, and for each fold we compute for the other fold that's held out the means basically, and estimate the mean of that outcome as a group, after grouping by these 6 columns. So it's non-trivial to do all that correctly, and we automated all that away so that we don't have to worry about that. Okay. Let's go look. Any other questions? I don't see any questions right now. Maybe I covered everything already. let's see what's missing. So we can diagnose this model on a new data set, but then you have to provide a data set with actual outcomes. In this case, the training data, for example, but that's of course going to be overfit because we just trained a model on it. So now it will say, hey, let me see how I'm doing on this data set, and it will say I'm doing really, really well because obviously I just saw that data set to train on. But that's what you can do. There is a deployments button which we showed you earlier. There is resources where you can download these scoring runtimes for the low latency or for the client APIs. You can also look at the system and see how many GPUs are busy right now or CPUs are busy. And there can always some message tabs so you can see what's new. And then you can see the release notes for every release. You can immediately see what's new, whether it's worth updating. I recommend updating within the LTS branch immediately. So if you're in any 1.8, go to 1.8.4.1. And next week we'll have 1.8.5. So every month or so we have another update on these. With small improvements. Sometimes a small new feature is added. But the big new features, multi-node and sharing, storage, that's all coming in 1.9 and then 2.0. And one more thing, you can try this for free for 21 days. You can ask for a license key on our website, and you can also get it for absolutely free if you're an academic license user. So for educational purposes, if you are at a university, you can ask for a academic license, and then you will be able to use this for free to teach your students, for yourself, to participate at Kaggle and so on.
Great. Well, thank you, Arno.
Cool.
I want to say thanks for taking the time today and doing a great presentation. I'd like to say thank you to everybody who joined us today as well. And the presentation slides and recording will be made available on our BrightTalk channel after the presentation's over. So we hope you have a great rest of your day.
Thanks, everyone. Thanks for your attention. Talk to you soon. Bye-bye.